So what do we use ATP for? We use ATP to make macromolecule anabolism. Remember, we keep talking about dehydration. Several glucose molecules, they can join together to form a glycogen. That is an example of dehydration, but it is also an example of anabolism. To build up a macromolecule. So we use ATP to do this. Transport work. We can pump substances across the membrane. Previously, we talked about sodium-potassium pump. The sodium-potassium pump uses ATP to move the sodium ion against the concentration gradient, and also to move the sodium ion against the concentration gradient from inside the cell to outside the cell. And also it pumps the potassium ion against the concentration gradient from outside the cell to go into the cell. Again, let me repeat. It pumps 3 sodium ions from inside the cell to outside the cell. And it pumps 2 potassium ions from outside the cell to inside the cell. Both are against the concentration gradient of the respective ion. That's why it needs energy, ATP. Mechanical work. You know, the sperm, they can swim, they can beat the flagellum. It's because it has lots of ATP at the neck area of the sperm. So that the ATP will supply energy for the movement of the flagellum so that the sperm can swim. Usually the reaction are coupled, not that we have only a few examples of reaction that occur alone. Previous example, we told you A plus B, the reactant together, they will form product C plus D, but they are usually coupled with the ATP so that it will release energy to provide energy for the conversion of A and B to C and D. So remember ATP into ADP, is it an antagonic reaction or exergonic reaction? Is it an antagonic reaction or exergonic reaction? I'll let you think about it for a few seconds. Okay, the conversion of ATP to ADP is a breaking of the covalent bond. When you break the covalent bond, it releases the energy stored in the covalent bond. Then that is an exergonic reaction. That means it releases energy. In other words, A plus B converting into C plus D, it will be by default antagonic reaction. Because one releases energy, one absorbs energy. This is another example that you will learn a lot more in detail in physiology, is the muscle contraction. Muscle contraction require ATP. Actually, specifically the hydrolysis of ATP will cause the muscle contraction. The reattachment of ATP, attaching ATP to the myosin, will relax the muscle. So from ATP, after the ATP is attached to the myosin, you relax the muscle, but the hydrolysis of the ATP into ADP will cause muscle contraction. As you can see that hydrolysis of ATP, or the release of ATP and inorganic phosphate, will move the actin and myosin filament across each other. It will shorten the length of the muscle so that we can contract. So it is like a cycle. Metabolic reaction, as I told you, that metabolic pathway is usually a series of linked reactions. They do not occur randomly, haphazardly. They have specific reactant and product, and usually the product of one reaction is the reactant of a new reaction. And they usually connect, the energy is captured and then it is released. They use it for successive steps. And during the metabolic reaction, we usually require the use of enzyme. Why? Because the metabolic reaction, if we do not use the enzyme to speed up the reaction, it will take forever. Then we cannot react to the environment so quickly. So enzyme is a catalyst to speed up the chemical reaction. Ribozyme, there are enzymes that can act as catalysts. Ribozyme, some people propose that it is like the first genetic material that developed by a prokaryotic cell, because it has the properties of a ribosome RNA, but it also acts as an enzyme. In chemical reaction. Enzyme, another problem is that it participates in a chemical reaction, but it does not use up. Meaning that we can reuse the enzyme again and again to speed up the same reaction, but enzyme can take up a different reactant. So after you convert A and B into C and D, the enzyme can bind to another A and B to produce C and D, and then after this it can repeatedly use because it does not use up by the reaction. So it does not cause the reaction to go forward. What it does is that it lowers the energy that required to produce the product. We'll talk about this later. So as you said, this is a more realistic metabolic pathway. So the reactant of one reaction become the product. The product of one reaction become the reactant of the successive reaction. If we're talking about enzyme, we usually call it reactant substrate. So enzyme and substrate will bind to the enzyme. Activation energy, that is important. This is what I mentioned previously. Enzyme does not push the reaction forward. It lowers this energy of activation or activation energy. This is the energy barrier that the reactant must overcome in order to convert into a product. What enzyme does is that it lowers the activation energy so that the reactant will have an easier time to convert into a product. In this case, when the activation energy is lowered, it increases the reaction rate. That means the conversion of the reactant into product will be faster, much faster and easier. So this is what happens when you use enzyme. X-axis is the progress of reaction. You can call it time. Y-axis is the amount of energy. So originally the energy of the reactant is here, and then the blue one is the one that is without enzyme, original reaction without enzyme. This is the product. You may call this A and B. This is C and D. The orange curve here is the reaction with enzyme. As you can see that the activation energy here, the hurdle here, becomes lower and smaller. So that the reactant doesn't need to go through as high as the activation energy here. You only need to go through this high, and then it can convert into a product. Therefore, it makes the reaction faster and easier. How enzyme function? So when a substrate, or we call it a reactant, binds to an enzyme, it binds to a site called active site on the enzyme. And when substrate binds to the enzyme, we call it enzyme substrate complex. Enzyme substrate complex. What happens is that it will cause usually it will cause a conformational change in the enzyme. That means the enzyme shape will change. And then the enzyme shape when the shape of the enzyme is changing here, then it will also cause the substrate to change into a product. Once the product detaches from the enzyme, enzyme will also go through another conformational change, and so that the shape will go back to its original form. Then when the shape goes back to original form, then it can rebind a new substrate, and then induce another conformational change to convert the substrate into the product. So this can keep on going. And that's it.